Hello, this is Eugene Chung. I'd like to show you a recent development I made for agent-based modeling or multi-agent systems. And this is a adaptive QuadTree for agents and emitters. So it basically manages the interaction and range query, object placements between agent to agents and also agent to emitter interactions. Now, how does it work? Well, in a really unoptimized landscape, without any QuadTree or other optimization techniques, you have the entire landscape, perhaps kilometers and kilometers of them, with multiple agents scattered around habitable areas. So, for a particular agent, there are 405 agents in this landscape. For this particular agent, if this agent wanted to do a range query, to see which agent is really inside its proximity for interaction, it will have to check through all the other agents. Okay, so all the other agents are, let's say, they are in a collection class. And there are 405 of them, so this particular agent will have to look through all of them just to check to see which agent is within its vicinity. Certain other agents like vegetation may have a smaller range, but still you have to look through all the all the other agents in the collection just to check their distances, so you get a range of objects within this, and that's not a very good optimized technique. So one solution is to build a QuadTree that partitions the landscape into chunks, and from those chunks you then do a range query and get the appropriate agent indices for interaction. My version of the QuadTree, I'll show you a diagram of this. This is a QuadTree agent emitter interaction. So when you start your simulation, you have a landscape, okay, and that's the root node, and there is a divide threshold. Over here it's 4, and there's a maximum layer which my version of the QuadTree allows. So you could actually set the maximum layer, so when it divides to those layers, it stops there, and all agents will be cascading down into this particular layer. So certain parts of the landscape, as we've seen earlier in the picture, certain parts doesn't really need to be partitioned, because, for example, in the Alps you have the high areas, and they may be rocky, or the slope may be too high an angle, or it may be in a very high altitude. So very little agent population will be in existence in those areas, but some other areas are more populated, and for those populated areas you might want to divide them more. So for example, in node 3 you have 3 agents there, and there's not a lot of agents, so there's really no need to partition them, okay, and it doesn't divide. So node 3 doesn't divide. Node 4 is divided into 4 child nodes, 17, 18, 19, 20, and node 20 is divided into more. So as they cascade down, the more agents there are, the more the nodes are divided, and that way these agents really need to only look through, have a range query of the nodes that are within this area and not the entire landscape. So then the computation will be lesser, it will be much quicker. For my particular QuadTree, I've programmed it so that it will only divide when there's a demand. So it's an on-demand sort of division of the landscape. You know, when there are no agents in that part, then you know that particular node isn't divided. And when the agents die, as you know, as is in the case of living organism, they reproduce, they die. The nodes will adapt to the needs. The other way of doing it, you know, I don't think this is a very good way, is to actually just divide, you know, all the nodes up to its maximum layer. So, you know, all these nodes, whether they have agents or not, are stored in the memory. But I think this is not the best way to do it. It will need to be tested, and I will do a test, you know, much later, just to see the difference in, you know, in nanoseconds. But that's the QuadTree structure, and that's how it works. So the divide threshold in the maximum layer, and also the boundaries of the initial landscape, is initiated, you know, passed in to the QuadTree structure. So you've got the top, bottom, left, and right of the boundary of the landscape with a maximum layer. The picture we saw earlier had, you know, 1, 2, 3, 4, 5 layers. So that's the maximum layer. And you have a divide threshold, and that shows that, you know, if there are more than a certain agents, you should start dividing the threshold. And there needs to be a test too, to see, you know, which threshold yields the best speed for a particular dynamic simulation. Well, the QuadTree really only has two classes. I've got the QuadTree manager, and you know, it's got, you know, a host of you look at the outline, you see, you know, a host. Oh, okay, let's close the outline. A host of functions to manage, you know, the size, manage the calculation, you know, object placement, range query of this QuadTree. On the other hand, you also have the QuadTree node, and the QuadTree node, it's basically just one node in that QuadTree, and in that node I manage the agent, which is of the type C organism, and also manage the environmental emitters, and this could be, you know, local temperature emitters and so on and so forth, and that's the C emitter node, and they are, you know, the child node of the C world object, which is here, which is a child node of the C renderable, which manages the paint in Java, graphics G paint, and that object is inherited from the basic C object, which is inherited from the object of the Java. So that way polymorphism occurs regardless of, you know, what agent. So for example, I could be having vegetation inheriting plant inheriting from vegetation, which inherits from the C organism and the C agent, and also herbivore, carnivore, and I could have a lot of other organisms. But let's not talk about that now. I might do a tutorial on how to build a QuadTree much later, and I've got a C++ version of this for much larger landscapes, and it's in OpenGL. You know, eventually I'm going to implement a distributed parallel processing of the QuadTree in Linux. But now let's have a look at how this QuadTree works. Look at that landscape, similar to the ones I showed earlier, and it's initially divided into 4 nodes, you know, as a start. And you see, you know, there are actually 8 levels here from 0 to 7, and that's because I passed in, you know, 8, and the divide threshold is 2. So this is an applet, and it's, you know, it's showing me that at level 7 you would have, you know, 21,845 nodes. But because it is adaptive, you know, not all the nodes are in the memory already, because it's on demand. As I said earlier, it's on demand division. So total number of nodes is 21,845, and the minimum quad size once you've divided till the 8th layer is 8, and these are the child nodes of the area, and the leaves are 1, 2, 3, 4, which is that. But once we started to include agents, you see it cascading down all the way until it reaches node 3, and if we keep adding agents, the landscape will just keep dividing until we reach the node 8, and it won't divide anymore, because that's the last node. So all the agents will be residing at the maximum level. Now notice that for the other nodes, they aren't divided, so when there's no division, they aren't in the memory. So but this node is available, but there are no agents in there, so there's really no need to divide them. Now we're going to just go on and divide more. We could even insert emitters with the right mouse button, and they will also divide, so the agents will interact with them. And notice that as I click, you get a range check. Okay, so whatever is within range, okay, will be there will be a range check, and so if the node is within this particular if any of these nodes are within the range of object 47, agent 47, and it will retrieve all the agents within this node. So all the other agents aren't interacted with, and you see this range query, in node 20 you have 0, 6, and 7. In node 22, which is here, you've got 8. In node 71, you've got number 1, and so on and so forth. Okay, so we can just keep dividing them, and you find that the landscapes are quite adaptive. If I run this simulation and let the plants really grow and reproduce, you see a lot of changes as agents die, as agents reproduce. There'll be a lot of changes in the landscape. But this kind of programming QuadTree will make it very efficient when it comes to agents interacting in the landscape. These are all plants, but eventually I'm going to have movements of herbivores and carnivores and predator-prey systems moving across the landscape, and having the landscape becoming adaptive to their movements. But this is in Java, so the landscape can be only in a certain large size, but in the C++ version, which is in OpenGL, it will be much larger, hundreds of thousands of kilometers. Okay, so that's it. That's the QuadTree demo I've been programming for the last few days. Thank you very much.